viewers, this is Mr. P, and you are onto ISIFE EDUBLOG. If you are new in this channel, just hit a subscription button so you can get notification each time we drop a video like this. In today's video, we're going to be analyzing, discussing, and then interpreting DCSSCE West African Examination Exam, which is called Waec. This is a part 1 video, which is going to be titration of the potassium manganate or potassium tetrahydromanganate 7 against iron 2 tetrahydrosulfate 6. Okay, that is for a part 1 video of this year's SSCE Waec examination. Okay, so this is for the introduction of this what we should be discussing in this video. Okay, here we're going to try to preempt the examiners and not actually going to review what we are not sure, but here this video is just for teachers and then students, most especially how to tabulate readings and then carry out the necessary calculations involving titration of this part 1 video. And then there's also going to be a resource or instructional material for teachers, maybe who are finding it difficult to understand and interpret this practical to their students. In this video, we may not be displaying the practical thing, but we're going to be assuming as in running it as alternative to practical, and most especially how the table of reading should be done, so that the students or the teachers will be well informed that the table is where the bulk of the mark is. So first, we are going to start with the table of value. Okay, we're going to start with the table of reading how to tabulate titration reading. This is more especially to teachers of chemistry, how we guide their students. I think I'll start with the teacher's reports. Teacher's report, where a teacher is expected to put in his or her reports as a titration. And that means the students writing his exam and the teacher, they will be at each other. That the teacher had prepared the solution, we carry out experiments, and they record the results, the report sheet. And then this student will be marked based on that report. So I would like to start with that because that is very, very important for teachers and as well as students. I think after that report, you'll see a report like this on the kind of A4, where they will state clearly that the teacher should record the concentration of for alternative A. Everything is all about A, then B, and then C, of course. But most especially A concentration in maybe in gram. You write it here. Maybe we have A is 1.58. We're able to put it here. Okay, and then B is 5.5 gram. We're able to put it here. Then you now see this, and then average. Okay, so the teacher is now here put the 3 experiments. Okay, the same concentration you prepare for the student, the teacher is expected to now run the 3 of the experiment. For this titration, which also you do know that varies up to school. In this video, we're going to be taking this as end point. Teacher will be able to get 18.00 in centimeter cube, and maybe the next one was able to get 17.90 in centimeter cube, and the third one was able to get 17 points, maybe 70 centimeter cube, or rather 80 centimeter cube. Okay, and then the average of these three. That is what the teacher is going to have here. Okay, so the average of these three will be here. So it means that the students are expected to have a very close range of these teachers and three experiments carried out. For instance, teacher had the first experiment, supposing it's 18.00, 17.90, that is in two decimal places, 17.80, that is also in decimal places. Okay, the average is 17.90. Okay, the teacher should be able to let the students know this, because this experiment is a complicated one. Redox titration, so that is not much exposed to this kind of practical work. All they know is acid-based titration, so there's a little bit challenging to them. So they need to have a clue on this, so that they will be in same range with that of the teacher. That is really failure will actually begins. So if that is my own average set collective, every student in a particular center should also get this plus or minus 0.15. That is, if the students are not getting exactly what the teacher average is, at least they should be plus or minus within this range. So this is what it should be. Now I'll give you an example. In a school where the teacher have this kind of obtain this kind of grading, and that means the students also the students should be within this range. Okay, 18.00, 18.10, 18.20, 17.90, 17.80. I think everybody should be on this range. Okay, so that at the end, the student average should be teachers only will either be this or within this range. I'll give you an instance. Like I said, I'll start with the table. Okay, but before the table, there is something that the student is expected to do, which is the student is expected to record the volume of pipettes. So the student is going to record volume of pipettes, which of course is called transferring pipettes. It should be recorded as a matter of fact, which is what, 25. Always keep it in decimal places. You can also make around this 0 centimeter cube. Okay, so this titration, like a redox titration, no particular indicator is using, but it can just for the purpose of titration in the indicator used. I think I'll explain it later. Let me write it as self. Okay, we are titrating this with this. And it does look that the two compounds are stable, very stable, so they cannot have a very fixed concentration. So actually, one of it is to be standardized, so as to give it a fixed concentration. Okay, now, so this is it. So, because it's a redox titration, this is oxidizing agents, and this is reducing agents. Okay? This is an oxidizing agent, being that it is going to accept. So you call it electron acceptance in this case. And then this is going to be an electron donor in this case. Okay, so electron is being transferred from this to this. So the one that gains electron, which is oxidized is reduced. So this manganese is here have a titration state of +7. In this titration, is going to reduce to manganese 2. That is the lowest oxidation state of manganese. And thereafter, iron 2 in the reaction. After donating electron to this, okay, it's being that this electron donor is going towards be the oxidized machine, being that it is an electron donor in the reaction. So electron is being transferred from iron 2 to iron 3. Sorry, from iron 2 to manganese. As electron flow from here to here, iron 2 oxidized, while manganese reduced. Okay, it's a very interesting practical. So that's what you have it. So the next is to have you should make sure you're very careful with this table. Avoid all kind of mutilation and not this person. And write everything in ink. Ink. This is how it will be. And make sure you don't carry out more than 3 experiments. This is experiment 1, experiment 2, experiment 3. So this is my box of experiments. It's my box of experiments. This is where my burette reading. This is my burette reading. Are you with me? Okay, this is the final reading. And not omit the units that's volume you have to measure here. Okay, this should be your initial reading, the units, and now you like this, and the volume of A use. Okay, before the table, I should be able to tell us something here that A is a solution of 0.0101. Okay, 0.0101 mole ADN cubed of KMnO4. And then B is a solution containing FeSO4, maybe of unknown concentration. Okay. Now this is information that is needed to fill the table, but the teacher had already prepared this. Okay, what I gave you was, I don't want to show this in this video, and then we'll find out the actual concentration of the iron 2 in this video. So but this is 1.58. So we're able to get this by number of moles, as molarity is the mass concentration, which is this over molar mass of this, which is 156 or thereabouts. So this divided by 156, that is 1 equals 0.01. There is a molar DAP of KMnO4. So this is actually going to be in the burette. This is the burette. This is the burette with 50 capacity. Okay, so in here is the intense purple solution. Purple intense solution of KMnO4. So this is KMnO4 as the titrant. So this is how this is calibrated. 0, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And this is 1. Okay. Then we don't know the volume of A, which is the titrant. This is why we are preparing this table, and we are able to carry out experiments 3 times to ensure that the values we obtain here, that some value here will be consistent or concordant. That is the essence of running 2 titration. This one is just mere formality. Maybe anyone here will serve as a control. But at the end, you have to choose two consistent value and titer as your average to know the volume of the solution whose concentration is known. Because in this titration, the concentration of A is known, while that of B is unknown. So we are running this experiment to now standardize this one whose concentration is unknown from one whose concentration is known in the reaction. So we already have this. This is what the experiment. This is how the experiment should look like. So this should be standing vertically with a clamp and with a retort stand. Okay, so the volume of this is known because we've already stated that the transparent pipette is 25. So we're going to now measure the volume of this pipette. The pipette is used by trying to suck the solution until it gets to that mark. The pipette looks exactly like this. Okay, with various sizes. Okay, let's see, this is where the mark is at 25. So you now have to put your mouse. Your mouse should be at this point. Okay, where you now suck the solution from a container containing a white or pale green ion 2. The solution goes in here to fill this up to this mark, and then it should stand like this. And then you now make sure that the lower viscous is ready. It's ready. And then that is 25. It is called transparent pipette because the content of this should be transferred immediately to the piece of aluminous flask or conical flask. Everything should be transferred here. And you're going to see a light or pale green. It is the volume that is here, which you've recorded. This titration is one in which that the KMO form need H plus ion to be able to reduce. So that H plus ion will be furnished or supplied even to Waec. But I believe every teacher should be aware that H2SO4 should be prepared for each candidate in a measuring cylinder, maybe 10 ml or 5 ml, so that we can actually pour it here to make sure that particular H2SO4 will furnish the reaction with the H plus ion. So in addition to the summation of the reducing agent, which is a H plus ion, is being supplied by adding maybe any amount of H2SO4 or concordant to this solution. In this titration, remember you don't use any indicator. At this point, one may start thinking of adding 2 or 3 drops of indicator here. The reaction will not need an indicator. The one that is acting as indicator here is the oxidizing agent, which is already intense purple in the red. It is already intense purple already. So it's going to act as our indicator. And the indicator itself, or the indicator is KMNO4 in the reaction. That means is having dual purpose in the reaction. Dual, or it's kind of is acting as both oxidizing agent in the reaction and also an indicator. In the reaction, it does 2 functions: as an oxidizing agent or titrant, and as well an indicator. Okay, now this is already the titration pattern comments, in which this is now fixed here, and the clip or whatever is here will now allow gradually to now mix with whatever thing we have in that iron, so that we now measure the volume. The volume is known with acidification to supply this H plus. As the reaction proceeds, anytime it drop off intense, whatever thing that is here is the sometimes this K is acting is a spectator ion. So in redox reaction, we are not mindful of K. So what is in here is MnO4. This time around is minus. And what is in here, we are not mindful of this. So what is now an active agent in this is ion. So ion. So as you are releasing the solution from here to go in here, as this drop in here, okay, let me use this as the green solution. As this purple solution drop in here, this particular place becomes purple or pink. As you agitate or shake, the purple spread and then disappear. The color goes back to be green. It keeps going, it keeps releasing the amount of this into this until the whole of this is used up. Once the whole of this is used up, any drop, that is where students should be very careful at this point. A point in this titration will happen where each drop will come and it will look like the color is trying to persist and it will fade. That point is very close to the end point of titration. So at that point, you should start learning how to use drop by drop until exactly when one drop of solution from here changes this. Because the moment this thing enters here, it turns pink, disappear. Once a drop enters here and the disappearance did not happen, that is to say that all of this has been used up. Then the oxidized agent, which is MnO4, in that case have now indicated itself here. That is the end point of the titration. There will be persistence of pink color. So the whole of this now turns pink. Once it turns pink, you stop titration. And the moment you stop titration, the reading, there are two readings here. The first one, which you started from here, is going to serve as initial reading. And then the one that you now read is the one that's where the solution will be able to change. That is the end point of titration. Why it is called end point? Because end point always comes with change in color of one of the solution. That is the end point. Okay? So that is to say that there is no more ion in the mixture that is reacting. So that means that there is an excess reactant in the mixture. That is why that particular pink color now has to persist in that case. So this is where end point of titration occur. Okay? So this is what we are going to do in this video. Now let's come back to this. This is a report from the teacher at field. So I have to now record this. Okay, the teacher is not going to use this at all. Okay, we use this as is provided in the paper. This also for this. So this is where the teacher has to record the study experiment he performed. So every student should be aware. But when they are not aware, they should carry out the experiment in a way to be very close to this teacher's experimental end point and the average. How shall I explain this after the table? So look at what is going to happen in the table. Supposing that I'm aware, so this is how the teacher was able to run his or her experiment. For me, I will decide. That's why every teacher in this video should know what to do to help the students, so that the teacher's endpoint or experiment or report should be in very, very close to that of the students. It's very, very important that because of the sensitivity of the practical. It's not like a normal acid titration where they already know that the indicator is used, already know that the indicator is this color in acidic medium, is this color in alkaline medium, and this is the color in acidic medium. So the students have not done this kind of, so 90% of these students that have to write this might have not done this kind of experiment. But the only thing that can be done is for them to have a clue to what the endpoint look like. So that when they are doing it in the hall, it will kind of be a confirmation towards the being informed. So now coming to this point now, this is what I want to choose for my experiment. I want to choose two. I want to use second and third as my average title. So for me, I'm going to go with these two. For me, I want to go with this. So these two. Okay, see how many we have. With the first one, we'll start with this 18. 18.10. Okay. With my calculator, I can just add 0. I can just add from 0.5 to 1.0 to any of these. So if I'm choosing this now, let me choose this and add 0.5 to this. I'll add whatever thing, any of this number here from 0.5 to 1, knowing fully well that one will not be used as averaging. Okay, then that one is this one, this particular one is serving as my rough intuition. You can take it like that. So if I add the 0.5 to this or this, maybe probably this, I should have 18.60 here. Okay, now filling the rest will now be very, very simple. In this video, I'm just going to want to teach the teacher what they will do to help the student, to guide the student down. We want to put up a very good table for this experiment. Okay, you're telling the students this is the end point. It is not the main. Some of them don't know what to do when the end point is given, so you should guide them to what to do here. They should know the range so that the student will not deviate. Why you will use this tool as your average volume of acid use is because of consistency. Now, the purpose of using this tool is that Waec insists that the consistency should be plus or minus 0.20 for the next reading. Okay? Between this and this, if you don't check the difference between what you have, the difference is either this minus this or this minus this. That's the difference between this and this is something like plus or minus 0.4, and it's not within this range. So this particular rule is voided. As far as this particular experiment this table is concerned, this is voided. This cannot be used. So if you use this minus this, you now see that the range is within 0.2. I think the range here is 0 plus 1, 0 plus or minus. This is absolutely very correct. Very correct. Okay, good. So let me start with this. Let me assume this to be my first trial titration. Then I decided to start from here. So make sure you record the initial in 2 decimal places. In 2 decimal places, what we have 0.00. Okay, now, so that means I'm going up. So I should be adding up. This unit 18.60. I want to encourage students to use 0.00 in all of this. Okay, in this video, for me, I think this is the only experiment in this table that I will use 0.00, because one thing with this every form of use, it should be a difference between this and this. That is final and initial. I cannot actually have this and have this here as it doesn't make sense, but it can stand in here. So some people also prefer that after the first experiment they carried out, the next experiment, like the final of the last experiment, the final is like what when the solution is being used, is being gradually mixed with what the point where the solution changes color. Let's say this is where it changes color. The next answer of the range is 18.60. That is the final. And this one is this one. This is okay. So that means this is this level. This you get this. So here, some people prefer that in the next experiment. Now, since the first experiment stopped, they will not want to continue from where they stopped. Yes, that one is also very nice. So here I can still use this initial for the next experiment. Here should have been 18.60. Okay, what I need to do is to just add all this to, okay, adding all this to is like 0, 8 points, this is 6, and this is 36.80. Okay, that means this should also go down here, very down. So let's add that this is where it is before the change in color. Okay, that's the end point of our second experiment. In this point, I'm not encouraged. You're not encouraged to use this here again, because the sum of this sheet will be beyond the capacity of it. This capacity of this is 50. So I don't think that's adding up this to get this. Shouldn't add up. I don't think you can do the arithmetic later. And possibly I'm trying to see the arithmetic can work. So at this point where you are here, you have to pour a solution again. Okay, like I said, don't try using this again. You can, as well use anything, maybe not 0.00. maybe preferably 1.002.003.00 is okay. Okay, so what should be here? This should be what? 19.10. To make sure that this is different, final, this minus this is this. So you see it's fine. This minus this is this. Okay, that is very, very clear. So this is how the table should be. Now if you look at my table, look at what the teacher was able to record. Let me now see if I will score 5 marks. Okay, for having the same like the teacher. As being that consistency that the difference shouldn't go beyond this. That is for every candidate that we are able to get the exact average of the teachers in the reports or within this range. I think this range is earning 5 marks automatically. If yours is dropping from the range, if you're not getting exactly that, maybe it's above this slightly, maybe plus is 0.20 afterwards. It's going down to 4 marks. Or yours is going to 0.25, it's 3 marks. Yours is 0.37, it's 2 marks. 0.45, 1 mark. And then half, so people can end up scoring 0. That's what they have. So for my, I have to check. So for this, my average here, my average volume of A is what I'm using this. Okay? 18.20 plus 18.10 divided by 2. I think that should give me 18.15 centimeter cube. I can check what's up with that is here. Okay, I will check. So what I do now, this is what the teacher will be able to get. So I may have not got that exactly what I did and end up getting for. We'll just check it. I have 18.15 minus 17.90. Okay, so the difference. So it's not a good score. Either I can't do otherwise. I get 3 in that regard. But some gets this, so that's why you have to stay within 17. If you get anything from here, above, so anything from here can give you either 4 or 5. But 3 is not that bad. Everybody may say that I'm scoring, that means to be cheating. So, but I'm very comfortable with this. There are so many other ways I can still get my mark apart from this. So that is what the teacher should be able to test me. So imagine that my O is this because I'm using a value that is way above that the teacher. I was not able to get 5. But I'm okay. I'm very comfortable with 3 because that is not the part I should score. There's another 5 marks somewhere. Okay. For instance, that is now for that I already have 3 marks already because I just got comfortable with that. Okay. Now ensure that every of this final finishing on this, I did not omit my unit is intact. So I also have mark for it. Okay? So it's mark for it. So let's say 1 mark. So I already have 3 marks. So I have 6/10 now. So now all of these are all 2 decimal places. So my mark is not going anywhere. I also have my mark there, which probably is what is maybe 2 marks. So already I have 3 plus 3, 6, 8. Okay, then maybe at the end I can end up scoring 8 over what 10 for the table like this. Just give 8 for the table, and then I'll go for the next section on this experiment. So the table is very, very important. I'm still going to be making reference to this. So my calculation now will be based on this 18.15. This is actually going to be volume of my acid. You can post these videos and go back to all of this that you have just seen now. Okay, So we can go to section B of this, which is going to be the calculation. Bearing in mind that this is also given. So from the information, from this information they gave us, okay, and then we're able to tabulate our correct reading, state the volume of the pipettes that we use, and explain why this is self or oxidizing agent. What then we will now have to do now, from this information and the results, you are now to carry out some numericals on the oxidizing agent is the KMNO4 and this. The practical work is done. This will be able to do the practical work very well, and then the calculation will be very easy. Okay, to pick up another mark from there. Okay. Okay, we're leaving this behind because it's going to be useful in the next part of the reaction. So I'm going to state the continuing part of this. So this is like equation A. So we're done with that. Let me assume that in this case we're getting 8 marks in this. 8 is okay. But let's also show how also we can get other marks from this. From the information given, from the information provided above, okay, calculates. Since the concentration of this is given already, so what else we see is calculate concentration of A, which is the oxidizing agent, okay, or KNNO4 in mole per GMQ. Okay, okay. Concentration, another one, concentration of B, which is the reducing agent of FeSO4 in, okay, concentration of B, okay, this time is, okay, sorry, there's a mix of something, so A is now, so this is going to be B, so we're changing this to reducing agent. Reducing agents, okay, so this is going to be FeSO4, because A is already given, so don't anything. So consider of B, which is also reducing agents, is this time N gram per GMQ. Okay, so now everything will be, okay, in this video that is happening, in the main exam question will be good the other way around, everything will be A now, but it's still going to use the same method. Procedure to also solve it. Okay, the last one also, same that B, let's do this video based on B this time. So, which is going to be the mass of Fe2 plus in solution B pipetted. Okay. Okay, sometimes mass of Fe2 plus, okay, sometimes they come like this, in this of the pipetted. Okay, so this is information now in the next part of it. So, if they want to see yes, so we'll use this space here to start working on this. But most importantly, we need more coefficient of oxidizing agents, reducing agents in the well-balanced equation. So, we shall look at our equations. So, we are able to try to form an equation. Look at this. We are not actually using this. It's spectator. So, the reaction will now appear this way. So, we have this MnO4 minus plus iron 2. So, here, remember that this changes from manganate 7 to the lowest state of manganate 2. Okay? This is what changes from lowest states of iron 2 to higher states of what? Iron 3. It's a redox reaction. Just show the main factor in the reaction. This is +7. This is +2. This is +2. This is +3. So from here to here, there has been a clear case of reduction. From here to here, clear case of oxidation. Okay? We break the equation into two. We want to know the whole ratio of this to this. So we can go ahead to find the concentration of P. So we start with this. So we break this equation, we break it into 2 half cells. One for oxidation, this one is for oxidation Fe2 plus, and here is Fe3 plus. This is redox reaction, just like any other redox reaction. Okay? You balance atomically and ionically. So the number of Fe is equal to the number of Fe on this side. But the number of charges is not the same to the number of charges. So what we do in this case, now look at the side that is having more charge. This side is having more charge. The difference in charge on this side is close to 1 to this. It's 1 to this side. So either difference in which is 1 E minus. Okay, that's understand it as E minus. Okay, this is E minus. It's like electron gain, which is 1 minus 1. This is like +3. This is like +2. So +3 minus 1 is +2. So technically this is balanced. So to the next step, we go on this. We have Mn4 minus. Then we have Mn2 plus. Okay, in this redox reaction involving an oxyanion, the group of atoms that's having oxygen attached to it. What we often do in this redox reaction, since we use H2SO4 conc, added conc H2SO4 in the pale green ion 2. So what furnishes that H2SO4 is, what furnishes that H plus is H2SO4. So in redox reaction like this side is going to carry this. This side is going to bear this. So this is going this side. This is going this side. So how do we do it to apply it to say plus H2O? Just because of this O4. Okay, so we need 4 of this to have this state balance. And then plus H plus, how many H plus are you having this side? It's 8. So you have 8 here. It doesn't look like the atoms in balance. Number of H, I don't have any same as H here. H not I, H here is H here. M is M here. O is O here. The same. But let's check the charge because as you're balancing the atoms, you balance the charge as well. Total net charge is 8 minus 1 is 7. So all of this reactant is 7 charges. All of this is plus 2 charges. So the difference between 7 and 2 is 5. Which side is not charged in the reaction is this side. So that's going as electron loss here as 5 E minus. That's 5 E minus coming up on this. This is 5 minus 5 plus 8 is plus 3 minus 1 is 2. So it tells. So it's balanced. So look at electron gain, look at electron loss. They must be same to cancel out the electron since the electron does not exist in the grave sense. So to get rid of that electron here, we're going to multiply here by 5 and this side by 1. So 5 goes here, 5Fe2 plus, this 5Fe3 plus 5E minus. 1 go here, 5E minus plus. Okay, it doesn't look like it to be all the same, but that's part of the equation. So here it's the same thing, here is the same thing. So in all of this is just to get rid of this, to know that free electron does not exist. So what is the barrier reaction look like here? So I get one from here. I get this one. I was able to join this from my rear and join the other one. So let me start with this. 5Fe2 plus 8H plus H2SO4 added plus Mn4 minus. Here we have 5Fe3 plus product plus Mn2 plus 4H2O. This is the equation for the reaction. Maybe Waec be merciful to keep this equation on the equation paper. But if they didn't do it, you can pause the video and look at the step, take it to get all of this. But this is the balanced chemical equation of this against this. I'm going to underline the mole ratio. Look at B. The mole ratio of this is 5. The mole ratio of this is 1. Okay? Then check if it's balanced. It's 5Fe. It's 5Fe. 8 plus 4 times 2 is 8. 1 mn. 1 mn. 04. 04. So the question is practical balance. So being able to know the mole ratio of B to A is this. So I'll write it here that mole ratio of A to B. This is actually my A. This is my what? B. So A is 1, B is what? 5. Please keep this in mind. It's very, very important. It's very, very important. Okay. So I'm going to write my volume of assay. So wipe this and then solve this part here. So my volume of assay from the table, from the consistent title here is 18.15. Okay. 18.15. Okay, so now we can now solve for I, counting what we want. Okay, I can now say from all of this, I say from the balance equation, mole ratio of A is MN4 minus or KNNO4, okay, to B, which is Fe2 plus or FeSO4 is which one goes first is this one. So it's 1:5. And let's use this using CAVA all over CBVB is equals to A is 1/5. Are you with me? Okay. So at this point we substitute. I would like you to try to tell the examiner each strategy you use to solve this process. Strategy now is that I have to translate this into numericals. So somewhere we are given that the concentration of acid was given us from the information. So this one is given already 0.0100 if I'm not sure. Okay? I'm sure times volume of acid VB is on the title, I think was able to show you to 18.1 from our table to consistent title upon CB, and this is what we're actually looking for, times recorded volume of liquid 235.00 equals to 1/5. Okay, so let's do it. We cross, tell them you want to cross multiply. So write it here, you don't need to do this. Okay, so the strategy here now is that we're going to use this multiply by this and this multiply by this. So you'll have 25 CB equals to, okay, this times this. Okay, so that is the rules of constant plan. So here at this point, I think we have to divide both sides by coefficient of CB, which 25. So this is 25 CB divided by what? 25 equals to 0.9075 goes by 25. So that's our CB going down 0.036 mole per DMK. You can pause the video and check how practically same principle, same method, just like acid-base titration. Only that we must trace a little bit to get more ratio. Okay, so this is what it is for this. Like I said, that day everything could be centered on oxide agents. In this video, we're going to just be treating of reducing agents. Okay, that's it. So you can pause the video and take time going through this. Okay, now in the next we're going to look at concentration of B in gram per dl, since we don't actually know the concentration. Sometimes this particular person will ask this different formula calculates maybe the value of X, maybe solution B is S gram of this. So in this case, you will be asked to find the value of the X. It is all the same pattern. So the question is asked in different. Okay, now in this next, already have a list will be given to you. They may be given to you in this form. Iron is 56, relative organic mass of iron 56, this is 32, this is 16. So we now run this. Okay, the sum of all of this should be able to be 52, but that information is very, very necessary to solve this reducing agents in gram per dl. Okay, let's do it seamlessly. Okay, in this case, we need just these parameters, okay? Already we know that molar concentration of, that is B, which by extension is FeSO4 in gram per dl. Sorry, mole per dl, this is molar concentration. Is what we just wiped out now because we got my 0.03. I think like this. Okay, that's what it is. Okay, now this is what it is. And then molar mass of B, which also by extension is producing agent. Is okay. I'm running like this. I just state it as 52. So what I'm looking at okay, what you're looking at is mass concentration, or is mass conc, or this case they refer to it as concentration of B in gram per dl. Okay, so let's take it to be what under X. So with this we now state this, therefore molar concentration, let me use it as molar conc, is equals to mass conc, that is mass conc is the second aspect of it. Sorry, okay, it is the third of it over molar mass. So we plug these values here and substitute. So let's bring it here. 0.0363 is equals to, we have this as X now over molar mass 1.5. So remember, this information will be given to you. Okay, so you cross multiply. So this is X is 0.0363 times 152. So your X now is 5. Your X now is 5.5. 5.52 gram. So the last point here is mass of Fe2 form. Okay, basically FeSO4 ionizes, we have this plus this. Okay, so this is what we want to find out. Okay, then take note that relative atomic mass of iron. I think it's 56. So it's very important for us to find this mass using it. Okay, now how many moles of this is associated into this? It is 1 mole from the equation. This is 1. It is also 1. So 1 mole of this gives me 1 mole of this. So equally. So that means the molar concentration of this is same thing as 0.0363. This giving this this giving x, because multiply it will still be the same thing. So x now is this times 0.0363. Okay, which is what? Mole. So now you know that this x now is like mole per liter, mole per dm. So volume of the pipette, the volume of pipette here is 25. So we're going to take this into 25. So if I should take it from 25, it does mean that it does mean that 1,000 centimeter cube of this already had contained 0.0363. So the volume of the pipette, how many molar goes in here? 25 cm cube. We do x. So we cross multiply at these points. So we have that this is 1000 x now is equals to this times this. So 0.907. Okay, that's what it is now. So we actually have to divide both sides by the coefficient of x, so that x alone now is x below 9 is 0.0009075. Okay, I'll write it here. So this is going to be 0.0009075 or 9.1 times 10 raised to the power of minus 4. Okay, which is mole. So this is this, but that's not what it asks us to find. It asks us to find the mass. Okay, now I'm looking for the mass will be very, very easy for us to very easy for us to do now. Okay, now that this is actually the amount that is in the volume of B. So what I'm now doing is that number of moles, this is my number of moles. Let me use a 0.00, let's put it here, 0.09075. Okay, that is it. Mass of Fe2 plus is 56. Okay, sorry, this one should be molar mass. So we're looking for mass now. So now, mass of Fe2 plus that reacted is x. Therefore, number of moles can be n equals to mass can be n over molar mass. So we plug these values in. So n here should be 0.0009075 is equals to m, which is this x over 56. So cross multiply. M is 0.0009075 times 56. M is 0.0009075 is 0.05008. Okay, so which is, okay, let me put it here. My final answer, mass of this in VP protein is 0.0508 or 5.1 times 10 power minus 2. Remember the mass of this is in gram. So you can give you an answer that in standard form. So this. Okay, this is how to interpretation goes. The most important thing here you take out from this video is how to prepare your table of values. Okay, like I said, this second part of the part 1, okay, may be for on the day of exam, may all be for oxidizing agent. But in this video, we want to concentrate it also. Even if it is on the other way around, you still going to use the same principle to solve it. Maybe in that day, they may not give you the concentration of oxidizing agent, and then they now see that the concentration of reducing agent is what it's giving. Okay, well, supposing that in that particular question they give you either of the concentration in gram per DMPO or in gram, maybe reactive mass in gram, and it does look like the two redox reaction, the two as A and B concentration is not given. There will be one is given in gram. There is no molarity. So what you do is to find the concentration of one by using mass or molar mass. So now you see area to find the other concentration. So this is how to go about this. You go through this video. If you are new in this channel, hit the subscription button because subsequent classes. So those of you that you still do alternative A, this is alternative A, and this is part 1. So in the next video, you are going to be seeing the part 2, which is going to be question number 2 on identification of ions or salts. Thank you for watching.